computation of error probability is simplified if we have some knowledge about how the decision regions look, and this is possible only in simple cases. With the increasing dimension of the message signal space, it becomes increasingly difficult to visualize these decision regions. So, we will derive an analytical expression for error probability in a general M-ary scheme. We have seen that map detection rule for AWGN channel is given by this expression, which can be rewritten as this, where Cj is given by this expression, and now we can go a step ahead and make it little more concise and define what is beta j. So, this beta j is equal to Cj plus cross correlation between xt and sjt, or the projection of xt on sjt. Okay. Now, without loss of generality, let us assume that we transmit message M1. Now, this implies that for the correct detection, beta 1 should be greater than beta 2, beta 3 up to beta m. So, this implies that probability of correct detection given M1 should be equal to probability that beta 1 is greater than beta 2, beta 3 and so on up to beta m. Now, we know the received signal xt is equal to S1t, because we are transmitting message M1 plus noise nt. So, your beta j is going to be S1t plus nt projected over sjt plus constants Cj. This I can rewrite as S1t sjt cross correlation plus projection of nt onto sjt plus Cj. Now, let us define rho I j equal to cross correlation between the signal SIT and SGT, correct, for all ij equal to 1, 2 up to m. So, these are known as cross correlation coefficients. So, when M1 is transmitted, your Bj will reduce to okay. Now, this can be rewritten as This is the constant. This out here are the components of the noise projected onto the n-dimensional message signal space, and we have shown that these are jointly Gaussian random variables, each with 0 mean and variance equal to italic n by 2, which is the power spectral density of the white noise, and being Gaussian we also shown that these are independent. So, what this implies that beta j, which is a linear combination of jointly Gaussian random variables. So, this implies that your beta 1, beta 2 up to beta m are also jointly Gaussian. Now, we said that probability of correct detection given M1 is equal to this quantity, correct. Now, remember beta 1 can lie anywhere between minus infinity to plus infinity, correct? And let us denote this PDF joint PDF. This is the joint conditional PDF of betas. Then we can evaluate probability of correct detection given M1 by m-fold integration as follows. Joint PDF of betas given M1 and integrated over betas. So, this can be rewritten as so, having calculated this, we would be required also to calculate the probability of correct detection given M2, then probability of correct detection given M3 and so on. So, we will be required to calculate these quantities . Once we have this, we can calculate the unconditional probability of correct detection as follows. This is a conditional probability of correct detection given Mj multiplied by the probability of Mj, j is equal to 1 to n, and once we have the probability of correct detection, we can evaluate the error probability by 1 minus probability of correct detection. Now, to appreciate what we have done here, let us take a simple example. So, let me say that I have an orthogonal signal set consisting of m equals signal energies S1t to up to Smt, and these are mutually orthogonal. It means that cross correlation between Sjt and Skt is equal to 0 for j not equal to k and is equal to some constant value E corresponding to the energy of the signal when j is equal to k. And we have seen that this by definition we could call it as rho jk, which is a cross correlation coefficient. And now let us make one more assumption, that all signals to be equiprobable. If we do that, let us try to evaluate the probability of error for this case, for the optimum detector. Now, because we have orthogonal signal set, therefore, your orthonormal basis signals are simply the signals normalized by the energy which also means I can also write Skt equal to root E times phi k t for k equal to 1 up to m. So, what this implies, that the vector representing the signal Skt, if you have that, let me denote it by this. In this vector, you will have, in this case, n will be equal to m, because we will have m orthonormal basis signal, and in this you will see that the component of this vector skl will be equal to root E for L equal to k and is equal to 0 for L not equal to k. Okay. Now, we know that map decision rule is given by this, correct. Now, in our case, the message signals are equiprobable and the energy of each signal is also constant equal to E. So, in this decision rule, this term basically becomes a constant and the only variable is this. So, what we could do is basically we could simplify this map decision rule and rewrite it as beta j tilt. We can drop this term where your beta j tilt is by definition equal to projection of xt onto sjt. Right. Now, let us assume that we are transmitting the message M1 without loss of generality, correct. So, I will assume that M1 is transmitted If I make this assumption, then my beta j tilt will be equal to your received vector will be equal to this now. So, this will be equal to rho 1 j cross correlation between this plus projection of nt onto sjt. and this I can rewrite it as now remember your SJL, this will be basically equal to root E only when L is equal to J, otherwise it is equal to 0. So what this implies that your beta J tilt is going to be equal to this quantity when J is equal to 1 will be E plus root E, that will be when L is equal to J, and you will get noise component N1 for J equal to 1, and for all other case this term will be equal to 0. So, I will get root E and J for J equal to 2, 3 up to M. Now, please note that N1, N2 up to Nm are all independent Gaussian random variables, each with 0 mean and variance italic n by 2, that is the power spectral density of the white Gaussian noise. So, what this implies that beta j tilt will be also independent Gaussian random variables, because these are jointly Gaussian random variables which are independent. So, beta j hat will be also independent Gaussian random variables with following properties. The mean value of beta 1 hat would be equal to this value, because the mean of this is equal to 0, and the mean value of all other beta j tilt would be equal to 0. And the variance of beta j tilt will be all equal to root E squared multiplied by the power spectral density of the noise. This is equal to E italic n by 2 from here. Fine. And now we know that all this beta j tilt are Gaussian random variable. So, we can write the PDF of this as follows. This is a variance divided by 2. So, 2 pi 2 2 cancels, e raised to minus this is E, and this is for beta 1 tilt, and beta j tilt, this will be equal to, the mean value is equal to 0. So, let us use this k instead of j for k equal to 2, 3 up to m. Fine. Okay. Now, beta j hat for all j, we have just shown that they are all independent Gaussian random variables. So, the joint PDF can be easily written for this as follows. Would be equal to the product of the individual PDF, because they are independent. This is the PDF I am writing for the beta 1 tilt. And then product of the other PDFs. This is what I get. Fine. So, probability of correct detection will be equal to m-fold integration of this joint PDF beta 1 tilt can take values from minus infinity to plus infinity. I get this quantity, and then I have product this integral out here. I will write it separately. That integral is b1 hat minus so this term out here, I am just writing it separately on this. So, this is what I get, correct. Now, this term I can just change of variable for convenience. I just beta k tilt, I make it equal to x, correct. So, this equation which I have here, which I have to evaluate, can be rewritten as follows. Simply I can write it like this, correct. So, this will be because m minus 1 terms will be there. So, this gets raised to this term. Now, I can simplify this term, and to do that we will use this property of the q function. We have defined q of y to be this quantity. This is nothing but the integration from y to infinity of a Gaussian PDF with variance equal to 1 and mean equal to 0. Right? And if I have in general this Gaussian PDF with the mean equal to 0 and the variance equal to sigma n square, then I can write this from here, and I can write this quantity equal to this. So, given this, I can simplify this quantity. So, using this relationship we can get this term, and this term basically I can write it in this format. So, this becomes equal to this term out here, okay, fine. And now, let me make one simple substitution. This term out here is substituted as z. If I do this, basically this expression which I have, I can rewrite it as now you can make one more substitution. This energy E, I would like to write in terms of bit energy. Now, bit energy is equal to number of bits which will be given by log to the base 2 of m multiplied by EB. So, if I do this and plug into this equation, I get my probability of correct detection given M1 to be of the form multiplied by this term. This term is equal to 1 minus dz, correct. So, this term I am just rewriting it out here. Now, note that that signal set is geometrically symmetrical. That means every signal has the same relationship with other signals in the set. What this implies is that probability of correct detection given M1 is equal to probability of correct detection given M2, probability of correct detection given MM. So, the probability of correct detection is equal to probability of correct detection given M1, correct, and probability of error, correct, for this is the probability of message signal going in the error, will be equal to 1 minus probability of correct detection, and that would be equal to 1 minus 1 by root 2 pi of this quantity. Now, it is interesting to see that this is difficult expression to evaluate. So, we can no closed form solution will be available, but we can plot it. Now, without going into any details, we can show that as m tends to infinity, the probability of error will tend towards 0. And if you evaluate that, you get an interesting result. If m equal to tending to infinity, we get this. Now, remember that signal power is equal to energy in the bit multiplied by the bit rate, that is RB. So, what it follows from this, that for error free communication, this should be greater than or equal to log of to the base of 2 equal to 1 upon 1.44, or this implies that from this relationship so your rate has to be less than or equal to 1.44 times signal power divided by italic n bit per second. Now, remember we had derived a capacity of a channel of infinite bandwidth, correct, as this additive white Gaussian noise, and we had shown that channel capacity turns out to be this. So, for a white Gaussian channel noise, the channel capacity C approaches a limit of this as B tends to infinity. So, for M-ary orthogonal signaling also we can transmit at error free data at a rate up to this quantity, correct, and this will happen when m tends to infinity. So, we have shown the relationship of what we had learned earlier with this example. So, with this basically we come to the end of our study on M-ary communication in additive wide Gaussian noise channel. Quickly let me recapitulate what we have done. First, we said that any complete orthonormal basis signals can be used for expansion of zero mean white process. Next, we saw that given a set of m message signals, we can always determine a set of n orthonormal basis signals where n could be less than or equal to m using Gram-Schmidt orthogonalization procedure. We extend this concept to show that a continuous additive wide Gaussian noise channel is an equivalent to a vector additive wide Gaussian noise channel. Then we derived for a general vector channel an optimum detector which minimizes the probability of error and showed that it turns out to be what is known as MAP detector, maximum a posteriori probability detector, and this detector reduces to ML detector, that is maximum likelihood detector, when all your message signals are equiprobable. Then we derived explicit MAP decision functions and ML decision function for the case of additive wide Gaussian noise. We also studied correlation based and match filter based implementation of the optimum detector, and we saw that match filter has an interesting property of maximization of signal to noise ratio at the sampling instant. And finally, we also saw that computation of error probability is simplified if we have some knowledge about how the decision regions look, but this is possible only in simple cases. So, we derived an analytical expression for error probability in a general M-ary scheme. So, with this we come to the end of the module on M-ary communication in AWGN channel. Thank you.